over 4 times 3 times 2. Right? And you see what happens. an is actually a1 over n factorial. An is a1 over n factorial. Okay. So, what does that tell me? What does that tell me? Let's put that back in here, right? What we figure out is that all the ANs are related to the first term. Oh, and actually, A1 is A0. Yeah, so I should go back. I can go back even farther. Right. So AN is actually A0, right? Because this is A0 over 2. This is A0 over 3 factorial. This is A0 over 4 factorial. Anybody confused by this? Anybody confused by this? Right? I'm just solving. You know, each of these coefficients is 0, and that gives me some information about the original coefficients. Okay. Each of these capital A guys is 0. That tells me something about the little a guys. What it tells me is that y is actually summation n from 0 to infinity a0 over n factorial x to the n. Right? Because a sub n, what we just said was a sub n is a0 over n factorial. And you see, it's e to the x, right? This is some constant times x to the n over n factorial. That's some constant times e to the x. Okay. Now, we also have this condition. Y at time 0 is 1, right? So since y at time 0 is 1, we see that 1 is a0 e to the 0. That tells you that a0 is 1. Right? So the answer, what's the answer? The answer is y is e to the x. Now you should be sort of laughing a little bit at this point, because you'd say, Professor O, we knew that, right? Because y prime is equal to y, right? Y prime is equal to y. That's to say dy over y equals, dy dx, y prime is equal to y. We can do our separation of variables, right? And you see that natural log of y equals x plus a constant, right? So y is going to be e to the x plus some times some constant, and then this makes the constant equal to 1. Okay, so you'd say, why didn't we use separation of variables? It's true, we could use separation of variables. But just to illustrate the this idea that you can solve differential equations by plugging in power series. This is probably the simplest example to do it. Yeah. Okay. Okay. Everyone okay with this idea? Okay. The idea is pretend that your function is a power series. pretend that your function is a power series, then plug it into the differential equation and see what power series it has to be. Plug it into the differential equation, see what power series it has to be. Okay. 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 I am going to let you try one. We have to do course evaluations today. So we only have a few more minutes to do this. But let me ask you to start trying this one. Y minus y prime equals x. Y times 0 is 1. Okay. Okay. So try to use power series to solve the differential equation. See how far you can get in, say, 3 minutes. 2 minutes. Okay, there's only a couple minutes left, I'm afraid. So before we have to do the evaluations. So let me run through it, and then you see if you got something similar. Okay. So again, what you do is you say, well, let's suppose that it's a power series, right? And again, y prime is going to be summation from 1 to infinity of n a sub n x to the n minus 1. So then you subtract them, and you say y prime minus y equals x, right? This one is from 1 to infinity, this is from 0 to infinity. you do the same thing, right? It's the same thing we did last time. You shift the indices. So this becomes n from 0. And again, you have to shift everything up, right? And what you get is summation n plus 1, a sub n plus 1 minus a sub n x to the n equals x as n goes from 0 to infinity. Okay. So now, what do you get? Well, you get, say, when n equals 0, when n equals 0, so what do you see? Sorry. Okay, so okay, so what do you see? That this polynomial, this function here, equals x, right? So here's our power series, and it equals x. Okay. So now here's what you do. You say, well, look, that tells me that a0, right? The coefficient of 0 is what? No. Right here you've got a0 plus a1x plus a2x squared plus blah, blah, blah. And that all equals x. Okay? So what you get is that a0 is 0, a1 is 1, a2 is 0, a3 is 0. Everybody else is 0. You see that? You've got this polynomial on the left side, you've got a polynomial on the right side. They're the same polynomial, and so the coefficients are the same, right? Over here, what we have is 0 plus 1x plus 0x squared plus 0x cubed plus da da da, right? So what you get is a0 is 0, a1 is 1, that's the funny one. a1 is 1, everybody else is 0. Okay. So what happens is that you say, okay, a0 is 0. That tells me that when n is 0, I get this is 0. a1 is 1. So that tells me that a2 minus a1 is 1, right? a2 is 0. So that tells me that a3 minus a2, I'm sorry, that tells me that 3a, this should be a 2 here, right? 2a2 minus a1 is 1, 3a3 minus a2 is 0, etc., etc. Since y0 is 1, that tells me that a0 is 1. Right, the constant term is 1. Right. So here we get a1 equals a0. Here we get 2a2 minus a1 is 1. So a2 is 1, right? a3 is a2 over 3, that's 1 over 3, right? a4 is a3 over 4, that's 1 over 4 times 3, right? a5 is 1 over 5 times 4 times 3, etc., etc. So in the end, what you see is that a(n) is going to be 2 over n factorial, right? 2 over n factorial. Right? For for n bigger than 3. So the first three terms, you get a0 is 1, a1 is 1, a2 is 1. And then after that, it's going to be 2 over n factorial. Okay, so what you end up with is 1 plus x squared plus 2 over n factorial, x to the n, from n equals 3 to infinity. So that's your answer. Yeah. Where does the 2 come from here? Well, this is 2 over 3 times 2. This is 2 over 4 times 3 times 2. This is 2 over 5 times 4 times 3 times 2, right? Which is 2 over 3 factorial. This is 2 over 4 factorial. This is 2 over 5 factorial, etc., etc. Okay, I'm sorry to rush you, but yeah. So let me hand out the evaluation forms. Okay. So.